Okay, thank you. Hello everyone. My name is Dragons G Coldwind. I'm the Dragon Sector team captain. This is Jurczyk. He is the vice captain of our team. We've been playing CTFs now for not a long time, as a team for about 1.5 years, and during that time we did stumble onto some interesting tasks which we would like to share with you today. So first of all, who doesn't know what CTF is? Okay, I see some CTF players raising their hands. So basically, as CTFs, there are two types of CTFs. One type is, which we play mostly, it's called Geoparty. Basically, you have a couple of tasks, ranging from 15 tasks to, let's say, 50 tasks, or even more than that. Each task is related to one area of security. Sometimes they are related to many areas of security. For example, cryptography, web security, exploiting low-level stuff, web security, steganography, and so on and so on. Basically, the CTFs are played now about every week or every 2 weeks on different conferences, or sometimes during different events, or sometimes they are just standalone events. And there is quite a big community, which I'm going to talk about later. So, what was CTF? Now what is Dragon Sector? Dragon Sector is a Polish CTF team. This is, well, all the guys who are in Dragon Sector. Hi, if you are here. As I said, we play for about 1.5 years. We do play internet CTFs, and we also travel to offline events. For example, this is a picture from Korea, from Seoul, where we scored 3rd place on CodeGate CTF finals. These are pictures from Geneva, where we scored 1st place in the Insomni Hack CTF. So CTFs are both on-site as our CTF now, on Confidence and online. Now, there is a global ranking called ctftime.org, so if you would like to start with CTFs, this is the place you want to go, because it first has a huge list of CTFs that are yet to come. Second of all, it has a huge write-up collection, which means if you want to read how you should solve a given task from the past, well, they do have a collection of links, and you can find the full solutions there. Also, we are Polish. In the Programista magazine, we have a section called Strefa CTF, where we publish write-ups from the tasks we solve. Also, there is a global ranking. This is an old screenshot, but we are still on top 1.
It's actually the current one.
Oh, it's a current one, yep. Thank you. So it's the current ranking, yeah, and we are top 1 in this ranking. So far it goes good. So, now I'm going to talk about some tasks, and Mateusz is going to talk about some more. We are also going to tell you about some techniques we are using for the solutions. Let's start with Mumble Mumble. It was a task from almost a year, well, I think over a year ago, from Boston Key Party CTF. It was just 100 points. 100 points, it means it's an easy task. However, it has won the award for the most hated task ever. Well, actually, there is no such award, but it was really hated. Only 2 teams solved it. I solved it, and another person solved it. So, what you got was a pickup file, and in that pickup file was a dump of Mumble communication. So Mumble is basically a client for, like, TeamSpeak, for example. If you know TeamSpeak, Mumble is really similar, but it's open source. And the dump had really high entropy. This is because actually Mumble uses encryption, uses TLS, both for the control channel and for the voice. So, and the encryption looked really solid. So we had a problem, because how to decrypt, well, TLS, how to decrypt AES, which is basically used all around the place, and it's supposed to be solid. But, well, we have nothing more than just the encrypted pickup. And we actually didn't know how to solve it. We tried to find a bug in Mumble, but this task was for 100 points, so that obviously wasn't it. So we changed our approach. Instead of trying to solve a task, we thought, if I would create a task like this, how, well, it must be solvable, because this is a CTF challenge, right? So how to construct a task which has encrypted voice over IP and make it solvable? Well, then I remembered this paper. I don't know if you have read it. It's Yes, We Can, Uncovering Spoken Phrases in Encrypted VoIP Conversations. It's basically a paper about looking for, problems using variable bitrate. Variable bitrate means that if you take sound and you compress it, then something is going to compress into, well, not too many bits. For example, silence is going to either not be sent at all or will compress to really well. But when you speak, you actually, well, it doesn't compress well. The packets will be huge. So, this was, again, 100-point task, so it surely wouldn't be speech recovery. So maybe something else. For example, Morse code. So this is a graph that actually Wireshark out of the box can draw. You just go into statistics and ask him for an I/O graph. And if you look closely enough, there are short bursts of packets and longer ones, maybe dots and dashes. So actually, we translated it to dots and dashes, and then we took the International Morse Code decoding table, and we got this. PBR, my ass. And this was the flag. OK, Python Sandbox. So Python Sandbox, it's an interesting idea that some programmers come with. It's basically, I have a Python script, and I want to do some, I don't know, calculations or allow the user to run some Python script in my Python program. So what the programmer would do in that case, he would create a Python jail or Python sandbox. For example, would create a character set whitelist or a blacklist, maybe a function, object, variable, or substring blacklist or whitelist. So if, for example, someone, the user sends you the code, and the code has this substring, then don't execute it, but if it doesn't have this substring, then execute it. So this actually spawned a whole new category of challenges on CTFs, which are quite interesting. Anyway, the basic idea is that the input you send is sanitized somehow. It differs from challenge to challenge, and then it gets evaluated and basically executed. So I'm going to talk about two tasks from this category. First one is Nightmare. It was from Plate CTF, not far ago, 1 month ago. Worth quite a lot of points. And so basically, when the code execution reached your code, you had only one object in the global space. It was stdout. You had nothing more, like no standard print functions, no dir, nothing. But you could use stdout and all characters that you liked, and some keywords, like for example exec. Also, that flag was on disk in an unknown file. You didn't know the file name. Usually you know the file name. Here you didn't know. But so you had basically to open, somehow execute code on that machine to list the directory and get the flag. You could only submit one line of code, but I'm not going to talk about it because it's actually really easy to compress code into one line in Python, especially if you have exec. So we start with stdout, right? We have this object. What we can do is, if we type dot and there is a, double underscore or class parameter, this is actually a reference to the class object of stdout, which is actually type file. So if you have a reference to a class, in Python you can construct a new object of this class. If you cannot construct a new object of class file, you can, well, read or write files, right? So for example, what we did, you could open proc self mem. This is, of course, the memory of the Python process. We opened it for reading and writing, and we could, of course, do all kind of seeks and reads. So how did we proceed with getting code execution? Well, we found in the God table the address of the system. This is not the Python function system. This is the C-level system function from libc. We found its address, because it is in Python's God table. And then we had written it under the fopen64 entry in God. Why fopen64? Because actually when we do this, when we open a file, well, it needs to open the file somehow on the C level, right? And what Python does, it calls this function. So because of it, when we created another object of type file, we passed it a command to be executed, because underneath it, when Python started going through the GOT, it got the address of the system function instead of the open function, so it actually executed this cat and, well, put out the flag. So yeah, again, going from std out all to code execution. Another task was called yet another Python jail. This was actually pretty funny. It had actually the blacklist of substring that you cannot use in the code was pretty large, and everything fun was banned. The character list, well, it allowed most of the interesting things, so you didn't really feel too much limit here. How did the code look like? Well, I'm actually not going to talk too much about it. The important part was that in the global namespace, not of your code, but in the global namespace of the real application, the external part of the sandbox, you had two variables, part 1 of a flag and part 2 of a flag. And then when you when your code was executed, only this divider function, this function here, was aliased as div, and this was the only thing you had in your global namespace of the code you run. So again, we start from div. Well, there is something called, there's a parameter of function objects in Python called func globals, and you could access the part 1 and part 2 of the flag using this ways. Well, actually you couldn't, because the globals was one of the banned keywords, so you couldn't use globals here. Therefore, we needed a different approach. So what we did, we created a new function called myfunc, and we did print with, well, part 1 of a flag and part 2 of a flag. Now, this obviously wouldn't work on itself because we don't have part 1 of a flag in our global namespace, because the namespace of our function is totally different from the div function namespace. So globals differ. These are two different globals, sets of globals. But Python has another property. It's called func code. It's actually a code object. Well, you cannot override in in the code object the bytecode itself, but you can override the whole func code object. So what we did, we took the func code, myfunc func code object reference and put it in, well, the div func code object, which means that when we executed div, it actually executed this. But since the globals are in a different property and the link to the global set of variables is in a different place, it's not related to the code object itself, then that means that div used our code with the real global set of variables. And this is how we get the flag. So actually, this type of task is really interesting because after I learned about it, I found, like, in a couple of days, 2 different products which were exploitable using just escaping from Python sandbox. Generally, using Python sandboxes is a bad idea. Now, this task was interesting, the one I talked about, because I played it with a little more, and I started just running from my code, running the main function again, like the main function of the real code. What happened was that the CTF admins at some point added some debug code in the main, and they never expected it to be run. But since I did run it, I got an exception giving me some obfuscated file name, like a really random file name. But I also achieved, Sergiusz from our team achieved file opening here in this task. So I opened that obfuscated file, and it turned out that admins were dumping all the solutions into this file. So thanks to me running main again from the code, I got access to all the solutions from all the teams, which didn't really matter because we already had the task solved, but what was quite interesting leak. Okay, so going further, let me just check the time. Okay, going further. VM, this is a really interesting task as well. Category was called pwning, which means low-level exploitation, and this is as low-level as it gets, basically, or 500 points, so really difficult task. And we did spend about like 20 work hours with a friend on this. So what we got just a connection, a TCP connection to a server, and the server said welcome and CMD. Now, we did know that this is a custom architecture VM. So this is not x86, this is not ARM, this is something that the task creator just thought out and, oh, I will create a new architecture. So we didn't know anything about it. And yeah, that's it. That's all we did know about the task. So we did some initial recon, and the results were that you could just type ls, for example, in that shell, and you did get a list of all the files that were in the emulated file system. And these were cmd, which was basically the shell, hexdump, which was a command which allowed you to dump text, well, actually binary files in this case, because almost everything was binary. Then there was BIOS bin, which was the firmware image from that VM. Exit, which is, well, quite obvious. VM bin, which was the ELF executable of this VM, but actually even if we tried to dump it using hexdump, we only dumped the first 4 kilobytes of it because the architecture didn't allow you to dump more than 4 kilobytes. Using hexpaste, you could actually create files on that file system and execute them, which was cool. But, well, you don't know the format of the opcode, so it doesn't really give you anything. Now, the flag file, you couldn't dump it because there was some control check somewhere, and you couldn't use hexdump to dump the flag. So we already knew that we somehow need to get access to this flag. Now, if anything crashed, you got an output like this. Well, it's pretty obvious that this is a registry value dump. So there were 16 registers, probably 16-bit, and well, you had their value if something crashed. So this is quite a lot if you need to decode the opcode format. So what we did, we downloaded all the files and spent next 5 hours trying, actually like by trial and error, to see what byte sequence, what bit sequence actually gives what changes in the registers. And also we tried to look in the files we dumped to see which sequences appear and where they appear and what sense do they make if they appear. So after 5 hours, give or take, we did have a kind of working disassembler for this architecture. Now, for example, this instruction was quite funny because, as you see, we called it multiplication or addition, and we didn't really know. And what we figured out just later that if you gave the registers from like the higher register first and the lower register second, then it was multiplication. But if it was the higher, the other way around, then it was an addition. So quite tricky architecture. So yeah, using this, the next 5 hours we spent on analyzing everything we dumped from the machine, and we knew after these 5 hours that actually the memory is split into two regions. The BIOS region, which is a locked area which you cannot access, and well, the rest of where our programs are running. Now, the BIOS area had all the system calls were implemented there. For example, opening a file, reading a file was implemented in the BIOS area. Probably the ACL check for the flag was there as well. So we needed to get somehow to this BIOS area. We spent the next 5 hours trying to look for a bug. What we found was like a lol WTF moment, because it turned out that there was a syscall to just change the log BIOS area. And we could make it smaller, like for example 1 byte, and therefore be able to overwrite all the BIOS. And well, once you have that, you can change the flag string in the BIOS, because there was a flag string actually there, to anything else. And when we tried to open the flag file again, it said, well, this is not the file I'm protecting, so you can dump it and whatever. Now, the fun fact was that this bug was not supposed to be there. It turned out I actually did talk with the guy who created this task afterwards, and he gave me the code to the VM, and he just slipped. Basically, it was a typo. It was supposed to be solved in a different way. But, well, this is how we solved it. Just a note, on CTFs, actually, unintended bugs are more common than you would suspect. Okay, worldwide something. This is the next task. Again, I'm going to check the time, and I'm going to actually skip this. The slides will be all made public, so you can take a look again. Geolocation was a funny one and a short one as well. Actually, well, you had all these different flags, and they were gray at the beginning. Now, each team had a token, and if you entered from an IP which is related to a given country to a website with your team's token, then the flag of that country highlights and you get 1 point. So 1 point for each unique country that you entered this page, right? Now, how do you lit all the flags? Well, you cannot probably lit all of them, but how do you get the most points out of this task? You could use Tor, which is quite obvious. You could use proxies, like old school list of proxies, go one by one and just enter the page. This gave quite a good result. Then there is something like ping back, link back, trace back, and so on. This is a mechanism that is, for example, in WordPress, and it allows you to, if you post a news and someone links back to you, then he notifies you that he linked your article, so you can place a link to his article. Basically, it works this way, that you make WordPress enter whatever page you give it. But the problem was that the HTTP certificate on the site that we were using was incorrect, and therefore no one wanted to go there. Another method is you call random people, like this is the number to this country, so we just dial it and, oh, hello, could you enter this page? Yeah, like really close to like scam calls, I think. Or you could ask on Twitter, like this guy did. So this was a tweet to Antarctic base. Now, what's even more interesting about it is that they actually replied. But sadly, they were like, not there. Yeah, too bad. But it was cool. Okay, and this is the last task I'm going to talk about. It's called DOS Fun for You. I'm not sure what the fun part is doing there. We didn't think so for the first 20 hours. We called it like this. Oh my God, WTF. It was basically, okay, so what was it? We were given a box disk image and a config for box. And we noticed that in that config there is the serial port, set to be available on TCP port. Now, we also got an external address and a port, and we were suspecting that this COM was available there on the remote server, of course. The promise was of 5 plus 5 points, which was really, really a lot, like 2 times the most highly scored task on that CTF. This is from the DEF CON qualifications from a week ago, I think. So this is, when we run it, this is how the application looks like. It's basically FreeDOS executing a custom police force management in Unreal mode. Who's familiar with Unreal mode in the x86? Yeah, so we actually were really familiar with it as well as you, so not at all. And we knew that the interaction was all via the serial port. So you couldn't click on it, you just needed to send something through the serial port, but we didn't know what. So the first 10 hours we spent reverse engineering everything. So so Unreal mode is actually 16-bit code with segments, which made it quite funny. But we managed to reverse engineer everything, and there were actually 6 packets. You could add officers to a list, delete officers from the list, add crime scenes to the list, delete crime scenes from the list, and also list all the crime scenes. So we reversed it, reversed the protocol. We created our own implementation in Python. By the way, Code Interactive Console really is awesome. And for the next 5 hours, we tried to look for an exploitable bug, because, knowing how application works doesn't mean you actually find the bug. We found 3 of them. A minor information leak, which was kind of useless. Then malloc not fully returning null on an error, because, there are 2 things here, the segment and the offset, and malloc for some reason only nulled one of them, not both of them, which means that all the checks if malloc was correct later in the code didn't work. Okay, I'm going to mention that later, sorry. And we did find a use of an uninitialized variable in malloc leading to a lack of update of the head of the list of the 3 blocks in the heap implementation. It was a custom heap, by the way, in some specific cases. Now, both these errors were not intended. The task author didn't know about them. And we decided to exploit the task using the second one. Now, so using some custom heap feng shui, this led to being able to control the list of 3 blocks, blah, blah, blah. And actually, we could overwrite 4 kilobytes of any segment. But this is not real mode. We cannot just overwrite memory. This is unreal mode, which means that code segment is protected. We cannot overwrite the code segment because it's not writable, which made it more interesting. So what we tried first, we actually found an entry in the GDT to be able to overwrite the beginning of RAM memory, of the physical memory. And as you know, there is the interrupt vector there in real mode and unreal mode as well. So we did overwrite like this interrupt vector and triggered like COM communication, and it triggered the interrupt, which jumped into our code. But we ended up in a really weird CPU mode where we weren't in the Unreal mode, and all the APIs were set to be using Unreal mode. We couldn't use BIOS API for some reason. So we decided not to go this way. What we did, we found another entry in the LDT section, which was a mirror entry to the code segment, but marked as a data segment and writable as well. So we could overwrite the 4 kilobytes of the code segment. And this meant that we could overwrite the functions that are there. So we just put the code which gets the flags, leaks them through COM, and then triggered the execution of that code. Actually, there is a write-up on the net about this task, and it's really, really, really long and crazy. You should check it out. It was a fun task, and Unreal Mode is fun as well. And that's it. Thank you. I'm giving this to Mateusz, who's going to talk through the rest of the tasks.
Okay, hello. So I would like to start with a task called curl core, which was a task from the Plate CDF this year, and it was medium hard. I have solved it separately to one of the other guys on our team, Valis, and I'm going to show both solutions. So when we downloaded the zip package containing the task, we basically found 3 files that were of interest to us: a pickup file, a GDB core dump, and a process memory map. So the background is that the organizers just used curl on their computer to download the flag over HTTPS, which of course was encrypted, and so we wouldn't normally be able to decrypt the flag, but we had the core dump which would help us to decrypt it. So the objective was to get the flag from the pickup file. Okay, so the initial recon was just to load the pickup file to Wireshark and see what were the parameters of the SSL connection that was established there. And we found the session ID that we could use later on. And we also found out that the cipher that was used was EAS 256. So nothing interesting, really normal stuff. So what Valis did is he downloaded the OpenSSL sources, grabbed for the master key string, and he found this very interesting debug code, which is enabled if you specify a specific define while compiling, and it would print out all of the configuration of every connection that is being established using OpenSSL. So it would give us the master key of the connection that we make using this modified version of OpenSSL. So Valis recompiled OpenSSL with these debug messages enabled and reproduced all the steps taken by the organizers. So he downloaded a file from the internet over HTTPS using this OpenSSL, and he found a master key because it was printed out by OpenSSL. He found it in the memory dump that he created, and he saw where the master key was basically where it was in memory and what was around in memory, and then he just took a look at the core dump that we received from the organizers, and he was able to locate the master secret roughly at the same memory area there. So we can see the key over here in the crash dump. So after we had this, it was just a matter of creating a key.txt file, dumping the session ID and the master key over there, and Wireshark is able to decrypt all of the communication using this information. So we got the flag. And so he solved the task like 30 minutes before me using this method. And so I decided to go more brute force way. So the EAS key that is being used to decrypt the information being sent over network is derived from the master secret. So I just decided to find the key and the IFAW value. So I knew about a few things about those values. So I knew they would be high entropy. I knew they should be somewhere in the core dump. I should be able to find them somehow. And so the question is, how many of such binary blobs of 16 or 32 bytes can be found in a 10 megabyte memory dump? Yeah, let's try to extract everything and see. So I used a very simple heuristic to find the high entropy blobs, because like all zeros or all ones wouldn't be really useful for me, and they couldn't be the key. So I just decided to take everything which is unique and doesn't have, like the most frequent byte isn't there for more than 3 times. And the result was that I found 4,000 possible keys and almost 8,000 possible IVs, which gave around 36 millions of possible pairs of those that I could use to try to decrypt the data. And that is a number that is possible to check. So I just created a simple Python script, taking all of those IVs and keys and trying to find the flag keyword inside of the decrypted data. And it took, I think, like 5 minutes before I found the proper key and the IV and the first part of the request sent to the server, because I just used like one of the packets that was being encrypted. So that was the task. It was very fun, and it showed that you can have any number of ways to solve a task, and as long as they work, they're fine. The next task, it was called Find a Key, and it's a task from the Olympic CDF from this year as well. It was pretty simple. So the task was basically over 100 lines of base 64 encoded lines. So when we decoded all of them, it turned out that they represented the contents of the Wikipedia entry for the steganography. So the first thing we tried was to try to decode all the text and then compare them like character by character, programmatically, of course, to see if there are any differences, because that might be the easiest thing to do for them, but it turned out not to be true. So the other question is whether they could encode any meaningful data in the way that those chunks were divided, for example, the length of the chunks themselves. But we couldn't find any useful information there either, and it wasn't so much information that could be hidden there, because there was only 100 lines. So the only other place that information could be possibly found is in the base 64 format itself, because there is no redundant data in base 64, and there is only one way to represent every piece of data in base 64. So the only place they could hide something is information that is being just ignored by the parser of base 64. So let's look into that. This is an image from Wikipedia of how base 64 translates characters. This is an example, of course. And so you can see that for 3 characters, you have 4 characters in base 64, or rather for 3 bytes, you have 4 characters. And it aligns very nicely, because 4 6-bit characters takes the same amount of space as the content that you want to encode. But the question is, what happens if you have a number of characters in the base 64 encoded stream that isn't divisible when decoded by 8? So you can have like 2 additional bits at the end of the stream, or 4 additional bits that are just being ignored by the base 64 decoder. It's just discarded. So you can hide information there, and we are pretty sure that they would do that, because that's the only place we could think of. So we wrote a very simple Python script. Python is, by the way, very good for those kinds of challenges in CDFs, and we extracted information. Like normally, the output for this script, when fed with data generated by a normal encoder, would be all zeros. But you can see a lot of interesting data here, so we were sure at this point that this is the flag, and when we converted this to ASCII, it turned out to be the flag. So these are the tasks that we wanted to talk about. There's also a few techniques. They are mostly related to low-level exploitation, because that's what I'm mostly interested in. So the first thing I wanted to talk about is the SSP leak. So I'm pretty sure most of you know about stack smashing protector that is implemented in Linux. It is a well-known mitigation against buffer overflows and other memory corruption on the stack. It was introduced a long time ago. It had different names throughout the last decade, but right now it is enabled using the fstack protector switch or the fstack protector all. So what it does is that, of course, it kind of restructures the stack layout to place buffers at the top of the stack frame and function pointers somewhere below and stuff like that. But the most important thing is that it tries to protect against buffer overflow by using a secret value that is put before the return address and the stack frame pointer. And then it checks the consistency of this canary before exiting the function. So this is the epilogue of two functions compiled with SSP on 32 and 64 bits. And so the interesting part here is the call to the stack jail fail functions. So you can ask what these functions are responsible for, and it turns out that when stack protector is triggered, it prints out some interesting debug information to standard error, such as the name of the application which crashed, the backtrace, and the memory map. So we would like to focus on the first line because it's of most interest to us. And so the stack check fail function body is really simple. It just calls 40 file fail with some string parameter. And so the most interesting part is here. You can see that libc argv0 is the reference here in order to print the name of the application. And an interesting fact is that argv0 is one of the pointers that is placed on the stack. It's high on the stack before the stack frame of the main function because it's inside of the libc objects, but it's reachable from within the buffer that is being overflown sometimes if the length of the buffer overflow is long enough. So we can possibly reach the argv0 pointer and override it before it is dereferenced by the stack protector. So you can see here, I just created a very simple example, just doing a string copy into a local buffer. And you can see that if you have under 200 bytes that are being that override the buffer and then the null, then nothing happens. But after that, the pointer to argv0 is modified. And first, it doesn't print anything because the modified pointer points to a 0 segment, and then it just crashes. So the requirements to use this there are a few of them. First of all, if you want to use this to exploit the vulnerability, you have to have the standard error redirected to a socket if you want to do it remotely, otherwise you won't get the information. The second important thing is that you have to have a long enough stack buffer overflow in order to be able to reach argv0. And unlimited charge set is also a very nice bonus in order to be able to specify any address you want. And with this, I think it is very powerful memory disclosure technique because like with no position-independent code, you can read all of the contents of the static memory in the process. And with a 32-bit executable, you can even brute force ASLR and read random chunks of stack, heap, and dynamically loaded libraries such as libc. And it turns out that the authors of CDF challenges actually thought of this and know about this, and this has been the way to solve a few tasks this year. So there was 2 tasks at CodeGate that we could solve this way. One was with an admin password in the static memory, which was very simple. The other one was with a secret string allowing for remote code execution in heap memory. So with that one, we had to run the exploit in a loop for 3 hours in order to be able to brute force the ASLR of heap, but we managed to do it, and we got RRC. And the third one was in plate CDF, and that was a really interesting one because there was a CGI binary that has a stack-based buffer overflow, so you would exploit it through a web browser, but then you would be able to, and so the CGI script would output whatever you want because of this leak, and since it would render it on a web page, you could use it to access as the administrator of the website. And yeah, there are 2 articles or posts on mailing list that already mentioned this. I don't know how much time we have, probably not too much, 3 minutes, well, okay. So I will probably skip most of this, but the slides will be available. Let's see. Yeah, so I think maybe this is interesting. So what we, in general, like the important thing to do in remote exploitation task is to call system bin_sh or something equivalent. And you know, you want to spend as little time as possible on exploiting those tasks. So you want to automate all of the things that you normally always have to do. And one of those is resolving the address of system. And so a very useful thing is creating a corpus of all available libc files that you can find in those CTFs. And you know that Ubuntu and Debian are the most often found systems. So you just pull all of those and create a database with all the symbols and offsets. So then you can, for example, like leak. If you have a leak in the task, you can read the .plt entries from the task, and you can get the addresses from libc and the offsets, and with that you can resolve any other symbol such as system, or you can leak, for example, a return address from the stack from main to libc start main, and then also use this to resolve the system address. So this is very useful. We have a lot of those files in Dragon Sector. Yeah, there are other ways too. So the corpus is not always enough because sometimes you have other libcs or other operating systems that we haven't thought of. And in that case, it is very useful to just have a Python script to resolve symbols for you, given a function that is being able to pull memory from the server for you. Okay. Yeah, you can also have some interesting techniques with regards to imports and drop gadgets, but you should check it out later on. And these slides are about the fact that instrumentation is a very interesting thing and very useful for CTFs as well. It's not always about patching. Patching is sometimes very hard and not so convenient. And instrumentation provides you the means to try to change the behavior of certain instructions without changing the memory at all, which is useful. And we use this, for example, to solve the OX90 task, which would just, you know, like loop over 10 trillion times. We're using expensive SSE instructions, and we couldn't afford to do it, but we also couldn't patch the binary because it was using the hash of the memory to compute the flag. So we just preferred to write box instrumentation, a few lines of code for box that would just check if the AX register is equal to something and then reset it, and also print out some useful debug data. And we run a whole operating system, a whole Ubuntu. Oh, this is the log console. This is the operating system. So we just, you know, converted a VirtualBox hard drive to a box one, ran the operating system. It took 20 minutes to boot, but it booted. And we ran the binary, and after another 15 or 20 minutes, it gave us the flag. So that was very nice. So the conclusion is that CDFs are fun, educational, and you have to know about a lot of things to solve the task, and it's good to have a diverse team because, yeah, everyone knows about something else, and of course, whatever works, works, and you don't really have to look for a way that the author designed it to be solved because there have been so many instances of tasks that we solved in another way. They intended us to, that it's, yeah, there are no good or bad ways. And that's it. Thank you. And do you have any questions?
Hey, do you share? Do you share your tool sets, the things that you develop to help you solve, or this is too competitive and you just keep it a secret?
It depends. So we have a blog. It's on blog dragonsec.pl, and we share a lot of write-ups there. So we don't publicly give all of our tool set, but we often share the tools that we wrote specifically to solve a given task. And it's like, on average, I think more than one task per week that is being described on the blog. So yeah, we try to share as much as possible.
Thanks.